Given, distinct positive integers candidates, and an integer target. Return, all combinations of values, with repetition, whose sum equals target. The example uses candidates 2, 3, 6, 7 and target 7. One valid combination uses 2 twice, then 3 once, 2 plus 2 plus 3 equals 7, reusing the candidate 2 from index 0 each time. The other combination is just the single 7 already in the list. Picture each candidate as its own slot with unlimited restock. For target 6 you could take 3 2s, or 2 3s. The trick is stopping before you overshoot the goal, not running out of copies. Treat target as cash left to spend. Each pick subtracts from that remainder. Exactly 0 means a valid combination. Below 0 means overspent, that branch ends. Without a rule, the same multiset appears in many orders, like 2 2 3 versus 3 2 2. We scan candidates in a fixed order and only move forward an index, so each multiset is listed once. Each step forks, take this candidate again so the remainder drops but the start index stays, or skip this value from here on by advancing the start index while the remainder stays for that skip. Search pushes until a hit or overspend, then undoes the last pick and tries the next option. That backtrack is what walks every valid combination. Here is the full recursion tree for candidates 1, 2, 3 and target 3, shown faintly. On the left is the input. A legend on the right will spell out what T and I mean on each node. We will rebuild the depth first walk step by step. Root state, 3 still to match, start index 0. We may branch by picking 1, 2, or 3 next, edge labels show the pick. From the parent we picked 1. Here remainder is 2 with start index 0, we may reuse that index or any index to its right in candidates. From the parent we picked 1. Here remainder is 1 with start index 0, we may reuse that index or any index to its right in candidates. Remainder hit 0. We record the combination, 1, 1, 1, this green leaf stays as one complete answer. The yellow edge labels from the root to this leaf read, in order, 1, 1, 1, that sequence of picks is exactly the multiset in the green output array. Remainder is -1, we overspent the target. No extension of this branch can work, so we prune this red leaf and backtrack. Remainder is -2, we overspent the target. No extension of this branch can work, so we prune this red leaf and backtrack. Remainder hit 0. We record the combination, 1, 2, this green leaf stays as one complete answer. The yellow edge labels from the root to this leaf read, in order, 1, 2, that sequence of picks is exactly the multiset in the green output array. Remainder is -1, we overspent the target. No extension of this branch can work, so we prune this red leaf and backtrack. From the parent we picked 2. Here remainder is 1 with start index 1, we may reuse that index or any index to its right in candidates. Remainder is -1, we overspent the target. No extension of this branch can work, so we prune this red leaf and backtrack. Remainder is -2, we overspent the target. No extension of this branch can work, so we prune this red leaf and backtrack. Remainder hit 0. We record the combination, 3, this green leaf stays as one complete answer. Following the yellow edge label from the parent, we only picked 3. That single value is the multiset written in the output below. We pruned every overspent leaf. Internal branching folds away. Only the 3 green leaves remain, the combinations 1 1 1, 1 2, and 3. N is the number of candidates, T is the target, and M is the smallest candidate value, all positive. Time is O of n to the power t over m plus 1 in the worst case. Each recursive level can branch over up to n next indices, and depth is on the order of t over m when we keep subtracting the smallest coin. Auxiliary space is O of t over m for the recursion stack and the current path buffer, matching that depth. The output list can grow with the number of valid combinations. That storage is separate from this auxiliary bound. Outer function, given candidates and target, return every multiset of picks that sums to target. We collect valid combinations in result. Path is the current pick sequence, shared across recursive calls until we backtrack. Call DFS at start index 0 with the full target as remainder, pass the same path and result objects. Return the filled result list. Helper DFS sits alongside combination sum, same nesting level, so languages without nested functions can map this directly. If remainder is exactly 0, the current path is a valid combination. Append a copy of path to result so later backtracking does not mutate stored answers. Return from this successful branch. If remainder went negative, we overspent and must abandon this branch. Return immediately without recording. Try every candidate index from start through the end of the list. Push the chosen value onto the current path before recursing. Recurse with the same start index so the same candidate may be reused without limit. Pop the last pick to backtrack and try the next index choice.